Okay, hello everyone. Welcome to lecture 5, Regulatory Landscape and Starting a Clinical 3D Printing Service. We will also have a guest lecturer, Martina DeSantis, who will talk on bioprinting. I have the same conflicts of interest as the previous lectures. So this is the outline for today. So we'll talk about the regulatory landscape. We'll talk about in-house manufacture. We'll talk about starting a clinical 3D printing service, some experiences that we have from Lund. I will shortly talk about biocompatibility, and Martina will talk about bioprinting. And then we'll end with questions and answers. So please post the questions on the chat as usual. So the regulatory landscape for clinical 3D printing, much is still quite unclear. What is really clear is that the 3D printing is challenging the regulatory paradigm. What I see is a shift from service providers that provide services for 3D printing to clinicians to a more point of care system where the printers are actually located at hospitals, and it is the hospital staff, employed by hospitals, that do the printing and the creation of models. And this is not only driven by the hospital itself, also some of the bigger service providers are actually driving this. What I see is a shift from, so they're actually driving this to, so they see that this is a future avenue, that there will be more point of care. Yes, so a bit on the European medical device legislation. So the current legislation is Medical Device Directive, MDD, which is from 1993. From May next year, it will be replaced by MDR, Medical Device Regulation. So it has a different legal framework around it. Actually, it was due to be replaced already now, this May, but it was postponed 1 year due to the corona situation. In short, each manufacturer of medical devices need to be certified against the ISO standard 13485, which is a quality management system for medical devices. The manufacturer also needs to follow other relevant ISO standards depending on the product. And they need to be yearly inspected by a notified body. And each product needs to have technical file documenting the product. And the requirements are different depending on the medical device classification. So each medical device is classified in different levels. In Europe, there are about 60 notified bodies, which are certified companies that are allowed to do the inspections. They have an hourly consultancy rate of about 200 to 300 euros an hour. For clinical evaluations, they charge maybe 600 euros, and that's actually in-house work, so it's quite fascinating that they can charge this much. A technical file inspection for a software product that is not too complicated might cost 20,000 euros. Yearly external costs for just maintaining. This is basically the inspections and formalization around that, and certifications, another 20,000 euros. And unannounced inspections that happens every 3 to 5 years, so they can come any day, anytime. Each such costs about 15 to 20,000 euros as well. And many notified bodies do not accept new customers as they are overwhelmed by the current workload. So in my perspective, I don't see that the European medical device legislation really works satisfactory. How does it look in the US? So in the US, it's regulated by the Food and Drug Administration, FDA. And each manufacturer or importer needs to be registered by FDA. in principle, it's the same guiding principle. What is a medical device as for Europe? And there are work both from the European side and the US side to try to harmonize the systems, but they are different, and they will continue to be so for foreseeable future. In the US, there's something called the 510K approach. So in that, the idea is if you have a new medical device product, you try to find a similar product on the market, and then you try to claim equivalence to show that your product is the same as the previous ones. If you have something that is really, really new, you need to have a different approach, which is much more complicated and costly. For the 510K approach, FDA have a 90-day turnaround time. So it's basically the time it takes for the first round to get the response. Yes, and probably try to avoid October, December, as then they need to answer you in around Christmas time, and they're typically more picky then. Regulatory aspects of clinical 3D printing. So all medical devices need CE mark for clinical use. And it's really the intended use of the print that determines if it's a medical device or not. So anatomical models for education, so they are not medical device. For instance, the needle guide that we developed for the ultrasound probe, it is a medical device. If you print an implant and implant it, it's definitely a medical device. It's either class 2B or class 3, depending on where it's implanted. Surgical guides, they need, they are medical devices. And the question is, are patient-specific anatomical models medical devices? So anatomical models in the US, the FDA says the following. So patient-specific anatomical models used to visualize or measure patient-specific anatomy in order to help to make a diagnosis or manage patient's health or treatment. Such usage are considered diagnostic, and the models are therefore fall under the medical device regulation. It's the opinion by FDA to regulate the software used to generate such models rather than the printers, but they recommend to include the printer compatibility information for the softwares. Clearance is not required if the software or printer is marketed for general use. In Europe, under the rules in MDD or the new rules in MDR, as far as I can see, anatomical models are not classified as medical devices. However, the software to generate anatomical models for clinical use are medical devices. There's something that's called in-house manufacture, and it's found in MDR and MDD under Article 5, Paragraph 5. And it says the following: with the exception of the relevant safety and performance requirements set out in Annex 1, the requirements of this regulation shall not apply to devices manufactured and used only within health institutions established in the Union, provided that all of the following conditions are met. So what I mean here is that you don't need to have all the requirements for CE mark if it's manufactured and used only within health institutions established in the Union. And of course, but still you need to follow the general safety and performance and requirements in the regulation. So in order to meet this, the devices should not be transferred to another legal entity. The manufacture and use of devices occur in the appropriate quality management system, meaning that the hospital needs to have a quality management system. And this is the most important C. The health institution justifies in its documentation that the target patient group, their specific needs cannot be met or cannot be met at the appropriate level of performance by an equivalent device all available on the market. So if there are other medical devices on the market that you can use and that but and your medical device that you manufacture inside the hospital is equivalent to those, you may not use this route for doing this. And this actually also explicitly includes cost. So even if you can manufacture it less expensive, this is not just a justification that is not should not use medical devices already on the market. And lastly, the health institution reviews experience gained from clinical use of the devices and takes all necessary corrective actions. So this is an exception that you might use for creating medical devices inside the hospitals. So if there are medical devices that are already on the market that do the same as yours does, then this can be hard to claim the argument under C. Here, so I should include some advices on starting a 3D printing service. So these are our experiences that are from Lund. So here's again the 3D printing center staff. So advice on starting a clinical 3D printing service. So first, try to get some seed funding to buy some printers, or actually funding to use service providers to do the printing, especially if you don't have that much experience with printing yourself. Try to print sample models or create some sample models, and invite yourself to present at different clinics. Typically, they have weekly meetings to get interest from the clinicians, and try to build a hospital network of interested clinicians. And this is also why you need the printed samples to bring with you and show this is how they look. And it's really important to feel the models and not only have a PowerPoint with you. In Lund, we right now have about 120 persons or clinicians on the mailing list and have regular newsletters that we send out. Try to prepare an upper management fact sheet or a deck of slides. Include a bit on decreased surgery time and potentials, and what that translates into cost savings, how it can increase, make healthcare safer and better. Some of the documented health technology assessments from the literature, and really try in this deck of slides to show a vision for the future technology. So it's a long work to get invited by the hospital management, but especially that's also why you need the large clinical network to help you promote this. Another thing that we found was helpful to take a photo of all printed models, especially the ones you do not print duplicates on. This is something I would have done more early on, to get a small photo booth that you easily can put on your desk to take a photo of the models. And we have several models that we printed early on, but and they are at the clinician's site, and we would like to have photos for presentations on, but we forgot to do it. So this is clear advice, to take a lot of photos on the models. As I said already in the beginning, to print copies of the old models for keep for presentations, and take a photo, as I said. May also do some retrospective cases, so maybe even do some cases even if the surgery already has been done. This also increases the trustworthiness of the technique, that you can show, yes, actually the model looked like it looked like on the surgery. So it helps you build trust on that. And you will learn a lot as you go, and do not forget to have fun. That's really, really important. Another thing that we used is to have a room where you don't deliver the models. The clinicians need to come and pick them. And in the same shelf you have other models, so they can see and get inspired from those models and see what others are doing. So it's really important to try to make the clinical 3D printing service a center where there's a physical meeting, And it's really when the clinicians come and pick up the models that the discussions are the best. They can discuss the models with them and how you could improve for next time, etc. A bit on our funding model. So we have seed funding from we started with seed funding from research funds, so Wallenberg Center for Molecular Medicine, and I had some ALF funding, which is national Swedish funding. And you really need to start from research funding, I think, because even if you can early on show to hospital management that you can save money on 3D printing, they will not invest it in any way. You really need to have some already have been started and say, yes, you're allowed to continue to expand. We received a grant from Region Skåne, which is the funding body for our hospital. There was a call for new technology to increase healthcare availability. So you need to think outside the box and see what kind of grants can you go for to make a center a viable option. Right now we have funding for 3 years. Thereafter there will be an evaluation. The plan for user fees is that we really see central funding as we see the center as a central resource for the hospital and not try to get 100% cost finance for each of the models that we do. So right now for 2020 we don't have any user fees. On 2021 it will be around 15% of the cost for the center in user fees, and in 2022 30% of the total cost. A bit on biocompatibility. So biocompatibility is a term that describe a property of a material being compatible with living tissue. This is ISO standard for biocompatibility, 10993. There's a set of standards. And there it says that it's the ability of a medical device or material to perform with an appropriate host response in a specific application. So they have two different classifications. One is on the contact duration, how long it is, and one of how the contact is. So first, the duration, it's considered to be limited duration if it's less than 24 hours. It's prolonged if it's 24 hours to 30 days, and it's permanent if it's 30 days or more. Then the category, how it's connecting to the body. It could be either surface, like intact skin, or next level is mucosal membrane, or breach, compromised surface, so such as wounds. It can be external communicating device, like blood path indirect, such as dialysis machine, for instance. It can be tissue or bone or circulating blood. Or the last category is implant devices, so tissue, bone, or blood. Most 3D printer manufacturers and material manufacturers have materials that are on some level biocompatible. It could be for skin contact. It can be food grade materials, so you can print your lunchbox, or it can be for breach or compromised surfaces. Typically look for materials labeled as Circle Guide or something similar, and request documentation or data sheets from vendors. And they're really happy to provide this, and you learn a lot by reading them. Very few manufacturers have materials that are classified for permanent, more than 30 days contact or implantation. And you also need to consider not only the material, but also the printing process. Can the printing process invalidate the material compatibility? There'll be some questions on sterilization methods in the course. So there are essentially 4 methods that you can use for sterilize 3D printed parts, the main ones. So it can be autoclave, which is a moisture heated gas, either 121 or 134 degrees. It can be gamma irradiation that you can use for basically all materials. The challenge for gamma irradiation is that it's expensive and equipment is not readily available. Then we have ethylene oxide, can also be used on more or less all materials. It's quite expensive and it's a toxic gas. Or you can have a formaldehyde, also toxic, but it's a fluid. So what I really recommend is try to use materials that you can be autoclaved, so then they need to be more temperature resistance. For FDM machines, we tried nylon. It worked on 121 degrees, but not the higher temperature. And now we use circle guide resin in our SLA printer. So now it's time for our guest lecturer. So I will stop sharing, and Martina will take over from here.
My name is Martina. I'm a PhD student at the Lung Bioengineering and Regeneration Group here at Lund University. And I'm looking forward on talking to you about 3D bioprinting, which is actually when you're printing your material together with the cells. So that's already distinguishing it from normal 3D printing, which is where you can add your cells later on. You can seed them at a later stage. So many of you have probably already seen images like these in the media. 3D bioprinted hearts, 3D printed ears that have been transplanted, or I should say subcutaneously implanted into mice, 3D printed retinas. And you've also probably seen headlines like these: 3D printed ovaries could pave the way for restoring fertility in women. We now have 3D printed human hearts. What a time to be alive. What a time, truly. So many of these studies, if not all, are proof of concept studies. So they're not closed yet to clinical translation. But that's not to diminish what they've done. They've definitely broadened understanding of the field in 3D printing and 3D bioprinting. And I'd like to talk to you on such a proof of concept study that we've actually done inside of our lab, which is my PhD project, which is on 3D bioprinting small airways with a hybrid Bioink. So first of all, why do we even want to 3D print lungs? There's many devastating lung diseases that still have no cure, and the end-stage option for many of these diseases is transplantation. But there's not enough donor lungs, and the survival rate after 5 years of receiving that transplant is only around 50%. So it's clear that new options for transplantation need to be explored. So what are these options? So people have been looking into bioengineering lungs ex vivo, and for that you need some sort of cell source that you can expand to an appropriate cell number, and you need some sort of scaffold, which is what we in our lab are looking into. And the idea is that you can then combine the scaffold together with the cells and ideally transplant that one day into patients. So if you look at the lung, you can see that it's complex across all the lung scales, from proximal, from the trachea to the distal lung. And you can see that it differs at each stage. So we'll probably need different materials and different manufacturing methods to bioengineer different parts of the lung. And so that's why a lot of groups have been looking into using biological scaffolds. So this is when you decellularize native lungs. So you remove all the cells using detergents and enzymes, but you retain the proteins, this extracellular matrix. And that's great in the sense that you keep this biological component. However, when you decellularize different lungs from different patients, what we've seen is that all of these patients, their protein profiles are different between each other. So that makes it hard if we're thinking of scaling that up for GMP manufacturing. So biological scaffolds are great in the sense that they retain the native environment, but reproducibility is an issue. And that's why many groups have also started looking into using synthetic materials. And that way you can have a high reproducibility, but it's also very difficult to actually mimic the native environment of the lung. So what materials and manufacturing methods can we use? This is here you can see a scanning electron microscopy image of a lung, and you can see that it's definitely very porous. So we'll need a manufacturing method for porous scaffolds, and that's where we think 3D printing could be very useful. Within our lab, we've thought a lot about what suitable bioinks could be for 3D printing lung tissue. And we've come up with a list of key characteristics that we think bioinks should have. So they should be compatible with the printing flow. They should be mechanically stable, especially if you're thinking of the inflation and deflation of the lung. They should be cytocompatible, pro-angiogenic if you're thinking of getting a vasculature in there, and they should be biocompatible.
Parts of this bioprinting lecture have been removed as they contain unpublished material by request of the presenter. These parts will be put back once they are published.
So I'd like to thank everyone in the lab who's been working on this project, all of our collaborators, and if you have, and of course you for your attention. And if you have any questions, I'm available now in the Q&A session, or you can also email me under this email address. Thank you very much.
Time for the Q&A session. So are you available, Philip? I can hear you.
Yes, so we haven't received a lot of questions. I hope that everyone who has a question will post them right now. The first question is from Finn. He asks, what about printing spare parts to medical devices?
Yes, very good question. So that's a complicated question. In general, it will be actually considered as a medical device. So either composite medical device or so. That's how I generally understand it. But I would say that this is one of the parts where the 3D printing really challenged the regulatory system. So we try to be pragmatic, but always do a risk analysis when we print spare parts. So for if we ever even think that this is sensitive, we do as an in-house manufacturer.
Yes, and mostly is for like if we talk about the needle guide, the needle guide that was presented from the company, the clinicians thought that it wasn't good enough. So there's also that aspect. But if you're talking about replacing like cogwheels in a X-ray machine, I think that's going to be a big problem, and I don't think that that is going to be a thing, really. So there's a question now from Eric. Would there be any regulatory difference between printing a 3D model to help plan for surgery versus using virtual reality or augmented reality to visualize the model?
Very interesting and relevant question. Yes, I would say, because for the augmented reality, you're depending on the software, and the software then, if it is for changing treatment or so of it, so the software then needs to be regulatory approved. And then the question is, does the physical model need to be approved? So this is really where it's challenging the regulatory paradigm. And the reason why the anatomical model in the EU legislation is not considered a medical device, is that it's not in contact with the patient, or it's not an active device.
There's a question from Sasidar. Does a 3D printer fall under medical device category?
So it's really depending on how it's marketed. So if it's marketed as something you use for medical use, it may be classified as a medical device. So consumer printers that you use, they are not medical devices because they're not marketed as something you use for medical purposes. So it's really depending on how you market it.
Yes. Marlu asks, when is CE certification needed for a 3D printed material and when not, resin or filament?
Again, it's depending on the indications for use. So if you say that it's not for medical uses, you don't need CE mark for that perspective. You might need CE mark for other perspective, being as a hazardous environmental. It might be for the persons operating the printer, etc. And those legislations might need a CE mark for that perspective. But you might not need it for the medical purpose if you don't claim medical usage of it. Was it somewhat clear? Because, for instance, if I buy a floating device for my kids when we are out on the sailing boat, those are CE marked as personal protective equipment. But of course, it's not CE marked because it's a medical device. So there are other reasons for CE marking things. And if all 3D printers are CE marked for electrical purposes, but it's another thing.
So Eric asks, thank you for a nice overview of the main important tasks in building a hospital 3D center. How long time did it take for you to go from start to where you are now?
I think you need to help me on that, Philip, but let's say you and I met December-ish or autumn 2018, right?
Yes.
And that's where we really started, and yeah.
Yeah, so we started doing lectures together, I think, in December 2018. That's when we also got our second printer, and then during the spring of 2019 we really started working. Yeah,
I really have built up a lot of prints, and we had this sort of a bit flying start because Philip was really already then the 3D printing nerd, running the printers, etc. So it depends on what you have. We also had the advantage of me being used to software and developing software, so we had that from the start. So that's gave us a head start, I think. And also we had the luxury of actually having research funding that we could allocate to this.
Yeah, we also had some very dedicated clinicians who really wanted to do some really advanced things.
Yeah, if you don't have that, nothing will happen, or not much at least.
And we don't have any more questions. One came now from Magnus. Does it mean a similar product, or is it exactly the product that shouldn't be commercially available? I mean, if something is slightly better or different, is it okay then?
And this is also why the 3D printing is challenging the regulatory, and that's how we are interpreting it. So if it's slightly better, so the needle guy is not fundamentally different, but it is an improvement that was that the clinicians thought was worthwhile, for instance. One thing that we're also thinking of is that, yes, you can buy some of the models from service providers for patient-specific models, or surgical guides, for instance. However, that process takes a long time, so you might not have the time, and that's a reason for building up possibility to do that.
And also in regards to the needle guide, the clinicians actually reached out to the company and asked them if they could do these changes that they wanted them to do. But they said no, it would cost them too much. So that was also like a verification that we could, since the company said that they wouldn't do it, that we could try and do it. So Eric asks, roughly how much does a standard model cost for you to print, for example, a heart?
This a good question. It depends on how you calculate. If you calculate either only the material costs or the entire cost, that's why I try to do the central funding system. So we'll have the salary cost anyway, and those are the most expensive. But let's say a normal size heart printed in a Formlabs printer, let's say 500-600 krona for material cost. So basically it's the volume of the model, and 1 liter costs between 150 euros to 300 euros, for instance. But if you really would try to find a cost model to get full cost, that would probably be at least twice the cost for salary and materials, and also to running the printer you need cleaning materials, so there are lots of more things. So yeah, most anatomical models will cost at least 100 euros. That's my guess, if we charge them this way. But it will definitely depend.
So there are no more questions right now.
So a bit on forward in the course. So one part of the course will be try segmentation of your own for those who are interested in working with that. So here our 3D printing center collaborates with this company Medviso to provide a course license of software. There will be an extra lecture on June 3rd by Carolina on how to install the software and how to get started with this. I will email out more details by email and on how to sign up for this. Otherwise, here are the schedule for the future cases. So it's on May 26th. It will be a bit introduction to the software and on orthopedics, and then we have different categories of application areas. And for all of these, we'll have one clinician to discuss how it works. Was there some more questions right now, Philip?
No more questions.
No? Okay. If there are no more questions, I will then end this lecture. So thanks a lot for today.